This is John Black, Super Chemist. I want to talk about a phenomenon that is a good way to isolate and extract carboxylic acids and also amines. Okay, I want you to look up here at this propanoic acid. All right, now I have it boxed off and I have this boxed off. There's a reason why. How do you make the salt of a carboxylic acid? Well, the same way you make any salt water. You react it with a base and an acid. Here's your acid, here's your base. We're going to use the Arrhenius acid so we get water. But you can use any of these. And you would get sodium propanoate and water, right? Now what's the difference between this and this? This is very ionic. It's a salt. So you know it's polar, it's ionic. This, however, has this tail here, okay, and hydrocarbons are non-polar, okay. Even though it has this polar end, you got most of it being non-polar. Now, the bigger the tail is, you know, when you get up to hexanoic acid, you know, past there, it's less soluble in water, but this is actually soluble slightly in water because of this polar end, okay. How do you make the salt go back into the acid? The same way you make any acid. You drip a stronger acid onto the salt of that acid. We already made the salt of the acid. So put HCl on, and there you go. The sodium chloride get together because they're very ionic, and the acid is made, propanoic acid. This is polar and this is non-polar. Same way here. This is non-polar and this is polar. See how these sides are polar, non-polar. Here's your amine, okay? Now, how do you make it into a salt or polar? You react it, you do the opposite. You react it with HCl, okay? Because it has these lone pairs up here. The proton will jump up onto the lone pairs, and you'll have an ammonium salt, okay? This is how you, this would be the way drugs are made, like cocaine or methamphetamine. The stuff that you would snort would be this salt, right? Any drugs that you buy in the store that's over the counter, they're usually a salt of an ammonium product. Now, how do you get it back to be, because this is polar, right? You can see it's got a positive here and a negative here. It's a salt. How do you get it back to be non-polar? You do the opposite of up here, which is a base, because this is your acid, this is your base. React them together, you get salt water, right? And then your amine goes back to being an amine instead of an ammonium salt. The only reason why I'm bringing up this is because polar and non-polar solvents are great for isolating these two things. I want you to think about in the video, right? I made my ethyl magnesium bromide from my Grignard reagent, right? And then I bubbled CO2 into it to make. Now, if you were using an aldehyde or a ketone or, you know, something like that, you'd make a tetrahedral intermediate, which is an alk oxide salt. Since we bubbled in CO2, it was trigonoplanar, and it made the salt of a carboxylic acid. But you can see it's salt. See how you're making a salt. When you get done with the Grignard reaction, no matter which salt you made, you quench it with HCl, right? Why do you do that? This is why, okay? Well, first of all, the salt is a weird salt. It's a magnesium bromide salt. So nobody wants that. The second reason is because you want to purify it. There's a lot of impurities in there. There's the ethyl bromide that didn't react. There's non-polar stuff. There's polar stuff. So you want to get rid of that, okay? Now, when you quench it, okay, you're turning it from a salt into an acid. Now, this was polar, now it's non-polar. You can see that piece for polar and ends for non-polar, right? When you add the water and the HCl, that's the polar part. The ether from the experiment is the non-polar part, right? The salt is now changed into an acid, so it will be non-polar, right? It will want to go up into the ether layer. okay? If you add table salt to this, you can salt it out even more, because it'll make it even less soluble in water. So you keep your non-polar stuff. The only problem is there's non-polar contamination in there, impurities, stuff that you made, stuff, you know what I mean, stuff that didn't react, blah, blah, blah. But you got rid of all the polar impurities. Now all you have is non-polar impurities, right? So if you take this, you put it down here, and you basify it with some sodium hydroxide, right? You're going to change it into the salt. You're going to move it. That's why there's not as many N's here, right? Because some of the N's are impurities, right? But some of them are the propanoic acid. And when you basify it, it turns into a salt and comes down into the polar region, right? So now you got rid of all the polar stuff up here. You got rid of all the non-polar stuff down here, and you are inside the polar solvent. But you did add some sodium hydroxide, so there's some polar impurities in there. Now you acidify it again with HCl, and you go back to the acid, right? And it would become polar. It would become non-polar, right? Throw some salt in there to salt it out even more. And now, since you've got rid of all your non-polar stuff up here, you have no non-polar impurities. They're all stuck right here. You have none. So the only thing that can be sucked out with the ether, right? Because you're going to add some ether. The only thing that's non-polar in there is your product, which is the propanoic acid. Then you can use your set funnel, and you have only your ether and your product. And you will have some water in there, so you put it in your set funnel. Add some saturated sodium chloride water, right? That'll suck out all the water, okay, or a lot of it. Then you take your ether layer and you put some calcium chloride or magnesium sulfate or something in there to soak up all the water, right? Then you can decant it off, and you got most of the water. You got, all the water out of there. Now the thing about the water is, see, if you don't get the water out like this, you can't really distill it water with the propanoic acid because it'll form an azeotrope. So you got to get all the water out first, so that you only have propanoic acid and ether. Ether boils at 34.6, something like that. Propanoic acid boils at like 141 C, something like that. That's over 100 degrees Celsius difference in those two boiling points. You can easily use a distillation apparatus and get that ether out of there, and what you're left with is nice pure acid. Okay. Now this is the same way with the amine, though. You have your amine, right? You would quench it and turn it into the salt, and you'd basically go back and forth, right? Now you have the salt part of it. You got rid of all the. Now you can freebase it, right? Get your amine out, because you already took all the non-polar stuff, impurities out of there. So the only thing you can soak up now is your amine, right? You soak up your amine into the non-polar solvent, and then you just bubble some HCl through it, and your product will precipitate out of the, say, benzene or whatever non-polar solvent you're using, and then you just filter out your product. It's pure because nothing else can precip out, right? So I just wanted to bring that up about how you can use this method to extract stuff. Alright, so what makes a polar or non-polar solvent? Well, one of the main things, but there's a bunch of factors, is the dielectric constant, or the permittivity of that solution. This is not a, there are exceptions to the rule, but anything less than 15 is considered non-polar. Anything greater than 15 is considered polar. Then you got your protic and aprotic polar solvents. Okay? If you have protons like hydrochloric acid or water, that's protic. If you don't have any protons like acetone or dichloromethane, then it's aprotic. But it's still polar. This just tells whether you have protons in the solution. Okay? I have DC, even though that does not stand for dielectric constant. In this case, it does. DM stands for the dipole moment, which is another indicator of whether you have a nonpolar or polar solvent. Okay, I have a couple of examples here. Nonpolar. These are the dielectric constants. This is the dipole moment. They're in dBis. That's the unit. But you notice, look at them, how they go up higher as you get to the polar stuff. Look how much higher they are. Then you get up, I only have one polar thing up here, but look, it goes up to 80, the dielectric constant. The higher the dielectric constant, the more you're going to go through this list. From non-polar to polar aprotic to polar protic. Okay? Same way with the dipole moment. If you have zero dipole moment, you're definitely nonpolar. Okay? There's no doubt about it. That's the best hydrocarbons. That's the best nonpolar there is. But I want you to notice, look at dichloromethane. According to this, anything less than 15 is nonpolar. 9.1 is less than 15, but we call it polar aprotic. Why? Because there's always an exception to the rule. Okay? It is polar because you can tell the two vectors, the horizontal vectors are going to cancel out, but the vertical vectors are going to combine. So you'll have a total dipole moment pointing straight up and down, right, to split these up. So there is polarity on this, okay? As you can see here, you got 4 chlorines here. All 4 of them can't. These two cancel, these two cancel. They all cancel out, so you have 0. That's why it's nonpolar. Same with this. If you only had 2 chlorines, it'd be polar. But you add this 1 chlorine in, and it kind of takes it down even lower from 9.1 to 4.8. And you can see the dipole moment goes down too. Just give you some examples of acetone. Look at that, 21. But you can see, like the dipole moment here should be lower than these. But look, this has a 2.91 and this has a 1.85. The dipole moment is lower, even though it should be reversed. But look at the dielectric constant. This one is the way it should be. This one's 21 and this one's 80. This is giantly more than that. It's 4 times as much more. So I'm just going over, this isn't really telling you anything here. I'm just little mix and match about how to choose your solvent, what's nonpolar, what's polar aprotic, and what's polar protic. You know, like hydrochloric acid, all your acids, mineral acids, are going to be polar protic, obviously. Okay, here's a list of dielectric constants and some things. You want to look at it, go ahead. One last thing I want to go over with solvents is solvents do play a big part in what type of reaction you're going to have. You know what I mean? Here's just a couple examples. Like, let's say you had an SN1 and an SN2 reaction. If you use a polar protic solvent, you're pushing the reaction towards an SN1. If you use a polar aprotic solvent, you're pushing it to be an SN2, right? The SN1 is the one with the carbocation, so the protons are going to help stabilize that carbocation, right? SN2, if you don't have those protons, right, you won't stabilize the carbocation. You'll go directly into an SN2 instead of forming that carbocation. It won't have the ability, like, to stabilize the carbocation with an aprotic polar solvent. Just like if you want an elimination, what do you use? You use a bulky base. You know what I mean? It's too bulky to get in to do anything other than take a hydrogen off. You know what I mean? And being basic, it always pushes it towards elimination compared to substitution. These are just a couple examples, but solvents play a big part in pushing your reaction to which type of reaction you would like. And that's pretty much it, because the video is more about how to get the salt of an amine or the salt of a carboxylic acid and make it go back and forth in between polar and non-polar solvents to purify it. And so have a great day, and always remember, science is great.